This video, we look at introductory physics question on equilibrium forces. Okay, so the question is saying in figure 4.8, okay, the pulleys are frictionless and the system hangs at equilibrium. We need to take into consideration each and every term being used. The system is first in equilibrium, meaning the sum of forces is actually equal to 0. If Fw3, the weight of the object on the right, this guy here, is 200 newtons, what are the values of Fw1 and Fw2? Of course, they've got answers here, but I want us to work out and see if they're giving us those same particular answers. Now, we need to know that since the system is in equilibrium, right? Since the system is in equilibrium, meaning the sum forces in the x should be equal to what? 0. One thing I want you to understand is that if I draw an axis here, okay, and here, like this, such that this is x and that is what? Y. You can see that the angles that we're dealing with, they are all attached to the y-axis. So this one is attached to the y-axis, even this one is attached to the y-axis. We know that x-axis always deals with the cos, right? Cosine. And the y-axis always deals with what? Sine. But since the angles we are dealing with, they are attached to the y-axis, we are going to swap them. All right, so the x-axis, instead, it will take the sine, all right, and the y-axis will take the cosine. That's what we need to understand, all right? When the x takes the cosine, it means the angle you're dealing with is attached to the x-axis. Same thing applies to the y. Now, the angle we're dealing with is actually attached to the y-axis, so these, they swap. They are normal representation of trigonometry ratios. Is it clear? Meaning, horizontally, all right, horizontally, to the left side, we have, now, let's just label. These are tension, these are ropes. So this is tension number 2, and that is tension 3. Okay, here there's also tension 1. But you understand what I mean. So all these forces are acting at this particular point there. Okay, they're acting at that midpoint of intersection there. So this side, we are going to have T2 sine theta. Okay? Plus the other guy here, remember these are horizontal. T3 also sine theta. Sine theta. Here the theta is 50, so this will be T2 sine what? 50 plus T3 sine 35. And we are saying this should give us what? 0. But remember, here's the thing. T2 is actually on the negative part of the x-axis, right? Meaning there's a negative part here. Meaning T2 eventually it will be negative. So because T2 eventually will be negative, we can just say that T3 sine 35 is equal to T2 sine 50. You agree, right? Sine 50. Careful on the signs. This guy here, automatically, it's going to give us negative because the x component here is negative. But this guy here, the x component is positive, and also the y component is what? Positive. But this guy here, the x component is negative, but the y component is what? Positive. Because it's going up like that. And this one is going like that. This one is going like that, and that one is going like that. Is it making sense now? So because of that, this guy, it will be negative, so we can just take the other side. Now we have this. We can make any of these guys the substitute of the formula. But we know what T3 is. T3 is actually 200 newtons. So I'm going to put 200 sine 35, which is equal to T2 sine 50. So T2 is equal to 200 sine 35 degrees over sine 50. Let's punch this together on the calculator. I'm getting 150, approximately 150 newtons. Now, we understand here to say tension actually equals the weight it supports. All right, the tension here is actually equal to the weight it is supporting. Therefore, Fw2 is also 150. Is it correct? Yes, F2 is here. F2 is there, 150, correct. Then we need to find T3. To find T3, We can also take now the the vertical component. Understand that in the vertical component, the sum of forces in the y should be 0. All right. And in the y, we have this friend of ours here. Remember that in the x, we never had this. But now we have this guy in the y, and it is negative, by the way. Okay. So it's like we have T1, okay, plus this guy here. Now remember, because the angles are attached to the y-axis, the y component, it will take cosine instead of sine. Get the concept, right? So we have T2 cos what? Cos 50 plus T3 cos 35. This should give us what? 0. That is what we are looking for. Okay? Now here's the thing. For the y component, both of them are positive, but this guy here is negative, this here, T1, because it is going down. It's pointing down. Remember that the weight of anything is actually acting downwards. So this friend of ours is negative. And because it's negative, we can just say that T1 is equal to T2 cos 50 degrees plus, okay, cos T3 cos 35 degrees. It's easier like that. All right, so then we can just plug in what we have. So T1 is equal to T2. We said it's 150. We just found it there. Cos 50 degrees. T3 is already given 200. Cos 35 degrees. Can you fail to find T1? T1, I'm getting approximately 260 degrees. Sorry, 260 newtons. And because we are saying the tension, it is actually equals to the weight it is supporting, meaning that FW1 is also equal to 260 degrees. Sorry, newtons. Why do I keep saying degrees? And which actually agrees with the answers given there. So this is how we actually use vector resolution in solving higher mechanics problems. So you are welcome.